Okay, a couple of other terms we use a lot is accuracy and precision. Here we got a marksman. The first marksman here, he's very accurate and very precise. This chap here, he's accurate but not very precise. Another word for precision is repeatable. So this chap here, he's got a goodish gun, but he's just not a very good shot. This fella here is an excellent marksman, but his sights are out, so all of his shots are just off to one side. And this fella here, well, he shouldn't be on the rifle range, really. He's a disaster. He's not accurate or precise. We have different types of errors. The first type of error we have is offset error. This is where it's out consistently all the way along the range. So, you know, you go up to, I don't know, some set of scales at the airport or something, and before you even put your suitcase on, it reads minus 10 kilograms. So you figure it's going to be out by minus 10 kilograms. The other type of error might be one, a set of scales, and you go up and it reads 0 at 0, but it goes further out the heavier the weight you put on it is. And that's what we call a span error, where at 0, it's okay. Down here at 0 is fine, but it just goes out as it goes up in value. So that's a span error. Another type of error we get is linearity error. We'd like to pretend that things were linear, that if we put one suitcase on the scales and one of the suitcases 5 kilograms, it would weigh 5 kilograms, and if we put 2 suitcases on there, it weighed 10 kilograms, and 3 would weigh 15. And we'd like to hope it was completely linear or in between, but in reality, very few things are totally linear. Most things have got a little bit of a linearity error. Probably the best example of linearity error is the petrol gauge on your car. Petrol gauge on my car tends to say it's full, it's full, it's full, and it just ran out. It's completely non-linear. When we're calibrating gauges, the old-fashioned gauges and instruments had 2 screws on them. The first screw, let's turn the volume up, the first screw was what we called the 0 screw. And what the 0 screw would do is it would adjust for that 0 error. For in the case of where we went to the airport and the suitcase, and even before we stuck a suitcase on, it was 10 kilograms out, we would adjust the 0. In the second example, where it was perfect at the 0, but it went out steadily, then we adjust the second screw, which is called the span. Fact of the matter is, when we're calibrating gauges, whenever you adjust the span, it throws out the 0. And whenever you adjust the 0, it throws out the span. So calibrating an old gauge that had 2 screws on the side was a constant backwards and forwards procedure. You'd calibrate the 0, you'd adjust the span, you'd adjust the span, and you'd adjust the 0, then you'd adjust the span, and you'd adjust the 0. And you went backwards and forwards doing this until either it read well or you got bored. And, you know, whichever came first, really. So you could go backwards and forwards doing this for hours and hours and hours on end, but mostly you didn't. With modern gauges, most modern gauges are to all intents and purposes just computers nowadays. So what we do with modern gauges is we just communicate to them. We plug our laptop in, and we have modern gauges give out, on the whole, 4 to 20 milliamp signal. So what we do is we say, okay, this is what we want you to, when this comes in, we want you to give a 4 milliamps, and when this comes in, we want you to give 20 milliamps. So for instance, if it was a tank, and I was measuring the height in a tank, I would say, okay, when the tank level is 0 meters, give out 4 milliamps, and say my tank is 7 meter high, so I've got a tank that's 7 meters high. When my tank gets to 7 meters, give out 20 milliamps. So all we have on a modern gauge is a computer that we communicate to, and we type in these two values. The LRV, which is the lower range value, which in my case corresponds to the tank is empty, and that's where I would get 4 milliamps, and my URV, my upper range value. Now my tank is 7 meters high, so that I type in 7 meters to give me 20 milliamps, and that's it. That's a modern system calibrated. That's all you need to do to calibrate a modern sensor, and it really is that simple. You can do 20 of them in half an hour. Another thing we're going to talk about is graphs. When you're plotting graphs, you generally got pairs of values to plot. And so you'll have a pair of value like 7, 9. Sometimes they'll be in brackets. The way to remember is that you go into the house before you go up the stairs. Now, I'm aware of the fact that lots of Australian houses don't have stairs in, but bear with me on this one. So just remember, you go into the house before you go up the stairs. Okay, and if you live in an apartment block, I don't care. Right, traditionally, input goes along the horizontal. If you have any time values, if you're comparing something against time, then you always put time along the bottom. You don't have to have everything plotted on the same axes, so that if you have time along there, you could have maybe valve position there, and if you're plotting flow as well, you could have a second axis with flow, because you might have a flow which goes up 0 to 10,000, so that your flow would be looking like this. If you plotted valve position on the same axis, well, it would just wibble along the bottom like this, and you wouldn't be able to see it. Whereas if you plot valve position on its own axis, you can actually get to see it, and you can see that there's a relationship between flow and valve position, which you'd kind of expect. With all graphs, the important thing is that we need to see the errors. We don't want you just to plot a single little dot, and then another single little dot, and another single little dot. That doesn't tell us anything, really. What we need to do, in fact, this whole course, the emphasis on this course is on errors and mistakes, because this is a maintenance course for people doing call-out, so it's the errors and mistakes that's what's going to get you your call-outs. So if we concentrate on the things that could have caused mistakes, then we'll get a hang of the things that could have caused call-outs. So to show errors, what we do is we plot the point that we found. And then we say, okay, this is the point that we found. In this case, it's 4.2 seconds. At 4.2 seconds, we made it 1.26 meters. But we have this plus or minus value. The seconds is plus or minus 0.2 of a second, and the distance is plus or minus 0.4 of a meter. So really, 4.2 seconds, it could have been there, and it could have been there. In fact, anywhere along that line. And 1.26 meters, that's what we found, but it could have been there, and it could have been there. So it's anywhere along that line. So in reality, the value could have been anywhere inside this rectangle. Sure, the thing that we noted, the thing that we first plot is this value, 4.2, 1.26, but it could be anywhere inside that rectangle. So when we plot in our graphs, we plot this Maltese cross. The Maltese cross I've plotted in red. And that Maltese cross lets us know how far out it could be. When you plot your graphs, it's very important that you never join the dots. If I have a graph like this, and say I've got volts coming in there, and I've got current coming in there, if I plot a whole load of values, and then I join those values up, then it suggests that the relationship between volts and current is not a straight relationship. It suggests that for a little while the relationship goes along like that, and then suddenly it gets to this voltage here and it takes a sharp turn to the left. And then it gets to this voltage and current here and it takes a sharp turn to the right. Now, I'm sure that most of us are aware that there is a relationship between volts and current, and it's actually a line going up like that. There's some sort of equation, I think, that relates them. So you don't join the dots. What you try and do is you try and fit a straight line, and if you've drawn your error bars in, that straight line should be able to touch all of the error bars, or at least all of the rectangles shown by the error bars. That's not a particularly nice drawing. If you can't obviously see a straight line, don't draw one. That's the best solution. When you draw your graphs, it's got to have a title, it's got to have a label on the axis, a label on that one, and if it continues indefinitely, say we have, say I'm plotting, well, volts against current, then volts continues indefinitely, not just where I left off doing the measurements. But on the other hand, if I'm plotting valve position, which is in percentage against flow, and I find that as I open my valve, my flow increases something like that, what I need to do is I need to stop my valve position graph at 100%. If I don't do this, what will happen is some accountant will come along and say, oh look, at 100% you got 20 litres per minute, so all we need to do is open the valve up to 200% and we'll get 40 litres per minute, because accountants are stupid. So what we do is we shut off our graph here with a block to say, no, that's 100, that's as much as you're going to get. Every now and then when we're doing our readings, we're going to get a funny value. There's a couple of reasons that this could have happened. It could just be that we are incredibly bad at doing our graphs. So, in fact, our error bars should be much, much bigger. So that if we do error bars like this, because there's a possible error, it'll all fit. It could be, on the other hand, that this is a real reading. It could be that in actual fact the values go like this. That's the sort of result you get from, for instance, a bandpass filter. So it could be a real thing occurring. Or on the other hand, it could be that there's a hardware fault. It's not that there's an error in the way you're recording or an error in anything you're doing. There could be a fault in the hardware that at this particular point the hardware just reads stupid. That's kind of like the first reason, but subtly different. Here's a table. Now those of you that have got books, and hopefully you'll all have books soon, this table is in your books, and I ask you to plot a graph, and the graph that you plot should end up looking something like this. So those of you that have got books, just a little exercise for you to do in your own time is to look at this table and plot the graph.